Hello students, good morning. I hope all are doing good. Good morning. Pratish, good morning. Good morning, Glasya. Good morning, Koteswar Rao, and good morning, Sohan. Good morning, everyone. Shall we start the class? Before starting today's session, I request everyone to be with the notebook and pen. Today, as I told you, we are going to start hybridization topic, which is really very important concept under chemical bonding. Okay, listen properly, follow the points properly, and if possible, try to note down the important points. Okay, and don't be diverted with unnecessary charting. Okay, don't be diverted and listen properly and follow the class properly. Shall we start the class? Are you ready? Yeah, good morning once again. Good morning, each and everyone. And students, please try to forward the video to your friends so that they can also take the class and it might be benefited for other students also. Yes, okay. If possible, Sushrutai, good morning. Once again, very warm welcome for today's session. In last class, we have discussed about day 2 bond. And in previous classes, we have completed ionic bonding and covalent bonding and various other possibilities. Okay. The remaining bonding, let's say hydrogen bonding, metallic bonding, and van der Waals forces or van der Waals bonding will be studied in future classes once you are coming after campus. Okay, so those bonding should be discussed only in offline classes, since we don't have sufficient time to discuss all the other kind of bondings. We have mainly covered ionic bonding, covalent bonding. Under covalent bonding, we have studied sigma bonding, pi bonding, and then we have finished even day 2 bonding also. Okay, I hope you are able to count the total number of day 2 bonds and covalent bonds which are present in a given compound. Fine, let's start the class. Okay, good. Okay, let's start the class. Yes. So today's topic is very important topic. Hybridization. I hope many of you guys will be knowing about this topic, and I have the best trick to find the hybridization of a given species within seconds, without using pen, paper, without using any formula. At the end of the class, I think after discussion about, okay, right, after discussion about important theory and important synopsis related to hybridization, I'll try to give a very useful trick to predict the hybridization of any given species. Okay, right. Now, hybridization is, before introducing hybridization, we need to talk about few things about overlapping of atomic orbitals concept. Under overlapping of atomic orbitals, we could be able to explain for only diatomic molecules properly. Let's talk about diatomic molecules. Diatomic molecules means the molecules which contains only two atoms. Okay, the molecules which contains only two atoms. You can categorize the diatomic molecules into homonuclear diatomic molecules and heteronuclear diatomic molecules. Homonuclear diatomic molecules means those diatomic molecules which are bonded with the same atoms. Let's say H2, Cl2, O2, N2, etc. When it comes to the heteronuclear diatomic molecules, let's say for example HF, HCl, HBr, CN, CO, etc. etc. So we can successfully explain the bonding between diatomic molecules based on overlapping of atomic orbitals concept. But if you apply the overlapping of atomic orbitals concept for polyatomic molecules, we could not be able to explain certain bond parameters. What I am trying to say, overlapping of atomic orbitals concept failed to explain the bonding in case of polyatomic molecules. Okay, then later on they have introduced a topic which is named as hybridization. So what are advantages for hybridization? The advantage is, what are the advantages of hybridization concept over the orbital overlapping concept? The main advantages are, we can explain the bonding, okay, and as well as shape or geometry. I refer to say, okay, of course, bonding includes certain bond characteristics or parameters such as bond length, bond angles, etc. We can explain. Okay, let me repeat this point once again. In previous classes, we tried to explain the bonding based on orbital overlapping concept. I have given this point also. Overlapping of atomic orbitals concept is able to explain for diatomic molecules properly. If you are trying to apply the overlapping of atomic orbitals concept for polyatomic molecules, we could not be able to conclude, or we could not be able to explain accurately. Then they have introduced the hybridization topic. What are the advantages of this hybridization topic? We can successfully explain bonding between atoms in case of polyatomic molecules, and along with that we can also explain the geometry or shape of a given species. Right? Now let us try to explore the important synopsis or postulates under hybridization. Okay, now continue. Important synopsis or points under hybridization. Okay. Number 1 point, look at carefully and listen properly. Very simple, very simple, since we need the theoretical background. Otherwise, I can directly go for calculation of hybridization of a given element in a given species. Okay. Right, hybridization can be easily calculated, but as we have to discuss about the theory, that is the reason why I am trying to give the theory related to hybridization. Right, the first point is that let us define hybridization. It is the process of mixing atomic orbitals. In short way, I will try to write them as AO. The process of Let me write even intermixing also. You can write mixing or intermixing. Intermixing of atomic orbitals to form new set of orbitals. If I am trying to refer atomic orbitals of nearly same energy, I can say nearly. It's better to mention this point also in the bracket. New set of orbitals with same energy. Same shape. Okay, is called as hybridization. Is called as hybridization. And the new set of orbitals are called as new set of new set of orbitals are called as hybrid orbitals. Let's try to understand the definition. Hybrid orbitals I prefer to represent as HO. What we are actually doing here, I'll try to illustrate the hybridization process in this way. Okay, listen properly. The main problem of orbital overlapping concept is direct usage of atomic orbitals. Now what I am trying to do, I am trying to modify my methodology to explain the bonding. Instead of directly taking these atomic orbitals into bonding, I am trying to intermix them before going for bonding. After intermixing of these atomic orbitals of nearly same energy, now these orbitals are modified into new set of orbitals. If I am talking about new set of orbitals, these new set of orbitals are called as hybrid orbitals. All the hybrid orbitals are having same energy and the shape also same. Right? Understood? I hope this point is clear. Okay, we are trying to intermix, like simply put all the atomic orbitals into mixer or grinder. Okay, if I am trying to intermix, how do you intermix the ingredients when you are trying to prepare a fruit juice? Okay, you have to mix the pieces of your fruit and sugar, milk and water, to all the important ingredients. If you are put it into the mixer, then try to apply the electrical energy, and if you try to mix them, after intermixing of all the ingredients, then what will you observe? After intermixing the ingredients of the fruit juice, then after completing, you will observe the same appearance, same taste, same color also. Here we are trying to do the same thing. The main problem arises by taking the atomic orbitals directly into bonding. Then what I am trying to do? I am trying to intermix them and I am trying to make the new set of orbitals. All these new set of orbitals are called as hybrid orbitals. Now these hybrid orbitals are having same shape and same energy. Right? Now the next point is very important point. Look at carefully. Number 1 point, I have given the definition. Number 2, these atomic orbitals should be from valence shell or any other inner shell. As we know that whenever we are going for bonding, we need to go for bonding by using only the orbitals which are present in the valence shell. As we know that valence shell is slightly far from the nucleus, you can reorganize the electrons only from the valence shell. Understood? Therefore, the atomic orbitals from the valence shell of central atom will participate in hybridization. Atomic orbitals of central atom, or otherwise atomic orbitals from valence shell of central atom. I used to write central atom as CA. Central atom will take part in hybridization. Will take part in hybridization. Students, patiently listen all the theories support background of hybridization. Then we will go for working questions. Okay? Right? You listen properly. Next, point number 3. Okay? It is not only the atomic orbitals with singly occupied electrons, that is, consider orbital with single electron, but also filled orbitals, means orbital with 2 electrons, and vacant orbitals, means orbital without any electron, can take part in hybridization. Can take part in hybridization. This point was very important for NEET point of view. Okay, NEET point of view, this is important. Okay, what I am trying to say here. So what kind of atomic orbitals of the central atom which are from valence shell can take part in hybridization? I was saying like atomic orbitals with singly occupied electron, atomic orbitals with paired electron, even atomic orbitals with vacant, I mean like without any electrons, can take part in hybridization. So if I ask you a question, what kind of atomic orbitals are going to participate in hybridization? Okay, so the orbitals with singly occupied electron, the orbitals with paired electron, and the orbitals without any electron can also take part in hybridization. Okay, just sorry to interrupt. Anshal, as I told you, we have discussed only ionic bonding, covalent bonding, and metallic bonding. As I told you, the rest of all different types of bondings would be discussed in future classes. So focus on the class and follow the points which I am explaining under hybridization. Next, moving on to the important point. Now, point number 3. Total number of hybrid orbitals formed. Total number of hybrid orbitals formed is equals to total number of atomic orbitals which combine together, or which are involved in hybridization. Let's say which are involved in hybridization, which are involving in hybridization. It means if you consider example, if I am considering, let's say, one s orbital is involving and along with p orbital, if we mix 2 atomic orbitals, we will get 2 hybrid orbitals. Total count of atomic orbitals is 2. And here, what do we get? How many hybrid orbitals you will get? 2 hybrid orbitals you will get. Hybrid orbitals count equals to 2. Since 2 atomic orbitals are involving in hybridization, How many hybrid orbitals are expected to be obtained? Only 2 hybrid orbitals are expected to be obtained. Let's say one s orbital and one p orbital are involved in hybridization. What would be the hybridization of the given species? The hybridization is sp, and how many hybrid orbitals I'll get? Only 2 hybrid orbitals I'll get. Okay, let us say if I am making s orbital and 2 p orbitals, one s orbital and 2 p orbitals. In total, I have totally 3 atomic orbitals. How many hybrid orbitals are expected to be obtained? 3 hybrid orbitals are expected to be obtained. So those are 3 sp2 hybrid orbitals. Why 3 sp2? Because 3 atomic orbitals are involved. 3 hybrid orbitals are expected to be formed. Since in this hybridization, one s orbital is involved and 2 p orbitals are involved, the hybridization would be sp2 hybridization. I hope the points are clear. If I am trying to take one s orbital and 3 p orbitals in the process of hybridization, in total I am trying to intermix 4 atomic orbitals. How many hybrid orbitals are expected to be obtained? 4 hybrid orbitals are expected to be obtained. What are those 4 hybrid orbitals? Let's say sp3 hybrid orbitals. I have written already 3 hybrid orbitals. I hope this point is clear. I hope this point is clear. Okay? I hope this point is clear. Understood? Have you understood this point? Students, give responses. Have you understood this point? Okay. So the total number of atomic orbitals which are involved in hybridization must be equal to total number of hybrid orbitals which are formed. That means number of hybrid orbitals formed can be inferred from the information about the atomic orbitals which are involved in hybridization. If 5 atomic orbitals are involved, 5 hybrid orbitals are expected to be formed. Okay. Next, the last point which I wanted to write over here is the possible shape of hybrid orbital is, if I am talking about the hybrid orbital, okay, if you consider maximum electron density is located or confined in most of the cases on one side only. Okay, located towards this side, located mostly on any of this side. Okay, on one side, let's say. If I am taking, let's say, s orbital is spherically symmetric. If I am talking about p orbital, if I am talking about here 50% electron density, here 50% electron density. But when I am taking the hybrid orbital, maximum electron density is located on any of the side. That means I can conclude this point clearly. Point number 5. These hybrid orbitals are more effective in forming stable bonds. Why these are able to form stable bonds? Since the electron density is located, maximum electron density is located on one region or like towards one side. If they are involving in bonding, the overlapping region will be more. If the overlapping region of the orbitals is more, strength of the overlapping is also more. If the strength of the overlapping is more, they are able to form stable bonds. Have you got this point? Have you got this point? I hope this point is clear. Since the overlapping region is more, then overlapping region is more means the strength of overlapping is more. If the strength of overlapping is more, then I can say bonds will be stable bonds. Okay. Next, the last point, which is really important point, is once after hybridization, these hybrid orbitals themselves, these hybrid orbitals align in space in proper directions to account the geometry of the given species. So therefore, we are able to explain the geometry also. Once after alignment of these hybrid orbitals, then the surrounding atoms' atomic orbitals will come and overlap with hybrid orbitals and forms the respective bonds. And simultaneously, I am able to explain the shape or geometry of the given species. Okay, that is the most advantageous part of the hybridization. Okay, so my dear students, let me quickly have a glimpse on the important synopsis which I have given under hybridization. You must know at least these points in order to study the hybridization. Okay, now my dear students, how to predict the total number of hybrid orbitals which are formed in a given hybridization? How will you calculate the total number of hybrid orbitals which are formed in a particular hybridization? You need to just count the total number of atomic orbitals which are involved in hybridization. Point number 1. All these hybrid orbitals are having almost same energy and all the hybrid orbitals are having same shape. And if you observe the shape of these hybrid orbitals, so maximum electron density is located on any one of the side. Let me say electron density is concentrated on this region. If this region is going for bonding, they are able to form effective bonds and these bonds must be stable. So I wanted to conclude one more point. If I am talking about bonding with hybrid orbitals and bonding with atomic orbitals, which is able to form strong bonds, can anyone tell me? Who is able to form very strong bond? Is it atomic orbital or hybrid orbital? Tell me students, respond. Students, please focus in the class, focus on the class and try to give responses. Okay? So tell me. So hybrid orbitals are going to form stable bonds or atomic orbitals? Who will be forming more strong bonds or stable bonds? Tell me. Give responses. Hybrid orbitals. Very good. So since, as I told you, the strength of the bond is depending upon the region of overlapping. If more region is involved in overlapping, and more will be the strength of the bond. Okay, good. Right, now moving ahead. Next, one point I wanted to write. Yeah, hybrid orbitals forms stable bonds compared to atomic orbitals. It is very important point. As I have mentioned under pi bond, let me quote this point also. This point was already explained under pi bond and sigma bond story. Okay, so listen carefully. Pi bond cannot be formed by, let me write otherwise, hybrid orbitals are able to form sigma bonds. Okay, hybrid orbitals do not form pi bonds. Okay, and the last one important point I'll write. Okay, how to count the total number of hybrid orbitals? Total number of hybrid orbitals. It means including what are involving in hybridization. I have given already total number of atomic orbitals. Total number of atomic orbitals. Atomic orbitals which are not involved in hybridization also there. Be careful. I am trying to write it is the total number of sigma bonds, and sometimes we may be coming across with total number of lone pairs. Total number of lone pairs. This is the very important shortcut method which I am trying to write. So just try to note down this point. We will use this in future, in next class most probably. How to count the total number of hybrid orbitals? It is the total number of sigma bonds, because hybrid orbitals are able to form sigma bonds only. Hybrid orbitals do not form pi bonds. We should exclude the pi bonds. And what can be included under hybrid orbitals? Okay, so hybrid orbitals are the orbitals which are able to form sigma bonds and the orbitals which contains lone pairs. Is this point clear? Is this point clear? After this, we will go for discussion about types of hybridization and we will go for examples. Okay? Have you got this point? Have you got this point? How to count the total number of hybrid orbitals? By knowing the information about hybrid orbitals which are able to form sigma bonds and hybrid orbitals which are not able to form, I mean hybrid orbitals I have given always used to form sigma bonds, and hybrid orbitals even can be counted the orbitals which are having lone pairs. Next. Okay, types of hybridizations. Okay, number 1, sp hybridization. For sp hybridization, what kind of atomic orbitals might be involved? One s orbital might be involved and one p orbital. P orbital, it might be x or y or z, etc. It is depending upon the nuclear axis. Okay, if I am talking about one s orbital and one p orbital is involved in hybridization, after intermixing of these two atomic orbitals, we will get hybrid orbitals. How many hybrid orbitals you will get in sp hybridization? How many hybrid orbitals you will get in? You will get in sp hybridization. You can write in this manner. Okay, how many hybrid orbitals you will get? 2 sp hybrid orbitals you will get. Right? Next, if I am taking, let's say, sp2 hybridization. In sp2 hybridization, one s orbital is involved and how many p orbitals are involved? One s orbital, and if I am talking about, let's say, this is one p orbital and this is other p orbital. Let us suppose this is pz orbital. Let's say this as px orbital. Okay, we are trying to intermix them. After intermixing these high atomic orbitals, you will get how many hybrid orbitals? 3 hybrid orbitals I will get. Next, in the same manner, if I am talking about the sp3 hybridization, for sp3 hybridization, you need to intermix one s orbital and how many p orbitals I supposed to intermix? Okay, let us say this as pz, px and py. Okay, if I am trying to intermix s orbital and 3 p orbitals, you will get how many hybrid orbitals? 4 hybrid orbitals. Along with, I am trying to give the alignment of these hybrid orbitals in shape. These hybrid orbitals will try to align in space with minimum possible repulsions so as to account for the shape. Okay, so this shape, if you are trying to write, what would be the shape of? So two hybrid orbitals are aligned in linear shape. Anyway, the shapes or geometries we will study. If I am talking about sp2 hybridization, these three hybrid orbitals are aligned in which geometry? Can anyone? Okay. This is considered to be trigonal planar. Trigonal planar. Have you got this point? Okay, understood. If I am trying to say, let's say, four hybrid orbitals are formed. All these four hybrid orbitals will try to align in which geometry? Students, anyone please? Anyone, any responses please? Now, if I am talking about the sp3 hybridization, in sp3 hybridization, if I am talking about sp3 hybridization, can anyone, what would be the possible geometry? This can be considered as tetrahedral. So therefore, all these four hybrid orbitals are aligned themselves in space with tetrahedral geometry. Okay, we can proceed like with 5 hybrid orbitals and 6 hybrid orbitals, etc. Let's say if I am trying to use 5 atomic orbitals for my hybridization, the hybridization is sp3d hybridization. Can anyone tell me the possible alignment of 5 hybrid orbitals gives what kind of geometry? With 5 hybrid orbitals gives what kind of geometry? Anyone please? 5 hybrid orbitals gives what kind of alignment of hybrid orbitals? Or all these 5 hybrid orbitals are aligned in trigonal bipyramid geometry? Okay, if I am talking about 6 hybrid orbitals, 6 hybrid orbitals can be aligned in octahedral geometry. If I am talking about 7 hybrid orbitals, 7 hybrid orbitals are trying to be aligned in pentagonal bipyramid geometry. Okay, very good, very good. Students, my dear students, there won't be any sp4 hybridization. As we know, we have only 3 atomic orbitals under p subshell. Okay, the maximum hybridization we can go for sp3 only. Then after completing 3 p orbitals, we are supposed to go for d orbital. Okay, so once again I am trying to give the possible shapes or geometries of the outcome of the hybridization, or after completion of hybrid orbitals or after formation of hybrid orbitals, these hybrid orbitals, they themselves align in proper directions. This direction of hybrid orbitals gives the shape of a particular species. Under sp hybridization, we will try to get what kind of geometry or shape? I can say linear. Under sp2 hybridization, what could be the possible geometry? Trigonal planar. Under sp3 hybridization, what will you get? Tetrahedral. Right? Now moving ahead, if I am trying to take, let's say, fourth one, which is sp3d hybridization. Okay, one s orbital must be involved and 3 p orbitals must be involved and 1 d orbital. Altogether gives how many hybrid orbitals? 5 hybrid orbitals. These 5 hybrid orbitals align in trigonal bipyramid. Okay, I hope this point is clear. If you want me to write, I will try to represent in this way, because I need more space. That is the reason why I am trying to squeeze this. Okay, there must be ears like this. If you observe ears in this way, yes, These are representation of hybrid orbitals. Understood? Okay. If you want me to make the possible directions, this is considered to be, as we have discussed, trigonal, planar, and over the trigonal planar we will have the representation of orbitals above the trigonal planar and below the trigonal planar. In future we will study these bonds are considered as axial bonds. These bonds are considered as axial bonds. Yes, this bond is axial bond, and even this is also axial bond. The rest bonds are considered as equatorial bonds. Equatorial, again equatorial, and how many equatorial positions are there in trigonal bipyramid? Equatorial. Right, if I am talking about, let's say, the fifth one, which is sp3d2. sp3d2. Here, how many atomic orbitals might be involved? One s orbital and three p orbitals and two d orbitals. Altogether produces 5 hybrid orbitals. All these 5 hybrid orbitals are considered as sp3d2. Sorry, 6 hybrid orbitals you will get. All these 6 hybrid orbitals are must be sp3d2 hybrid orbitals. I can say these hybrid orbitals as sp3d under sp3d hybridization. Under sp3d2 hybridization we have 6 hybrid orbitals, and then the last one is sp3d3. As I told already, these hybrid orbitals must be arranged in this way. Okay? If you consider, it gives kind of square over here, right? If you try to join them, it gives good. Now I hope you are following. Right, after joining these lines, you will get octahedron or octahedral geometry. So what geometry can be expected under sp3d2 hybridization? It is sp3. It is what geometry can be expected under sp3d2 hybridization? Octahedral. What geometry can be expected under sp3d hybridization? It is trigonal bipyramid. Shall we move forward? Shall we move forward? I hope you are following the points. Okay. So in today's session, I have given the basic theory, background and important synopsis under hybridization. From tomorrow onwards, we will work on prediction of hybridization of a particular element, let me say central atom for a given species. So we will calculate prediction of hybridization, and thereby we will try to predict the geometry of a given molecule also. Let me finish the last one. Have you completed this? I am trying to move aside this way. Okay, is it okay? Next, moving on to the last. Now I have, let's say, sixth, which is sp3d3 hybridization. If I am talking about sp3d3 hybridization, which is expected to be formed by combination of one s orbital and three p orbitals and three d orbitals. All together, after intermixing, you will get in total 7 hybrid orbitals. 7, let me write sp3d hybrid orbitals, sp3d3 hybrid orbitals. All these 7 sp3d3 hybrid orbitals aligned in pentagonal by pyramid. Okay, right? So if you want me to write the bond angles, don't worry, bond angles I will explain. Okay, I hope if you are able to identify the bond angle, it is well and good. Let me introduce the possible geometries, then thereby in tomorrow's class we will work on hybridization followed by bond angle, all the stuff. If you want me to just recollect, I'll recollect all the bond angles too. Fine. Okay, when I am talking about pentagonal bipyramid, let me write in this way. Consider here 1 and 2, 3, 4 and 5. Okay, totally 5 hybrid orbitals. 1 and 2, 3, 4 and 5. Okay, and which is one above the plane and then other one below the plane. If you can join all these, 1 over here, 2 and 3 and 4, sorry, okay, done. Okay, join all these lines. If you join all these lines, you will get a pentagon. This is pentagon, and above the pentagon there is one bond and below the pentagon there is another bond. Done. That is the reason why this kind of geometry is considered as pentagonal bipyramid geometry. So I hope with this I am going to close for today's session. Students, please thorough with all the shapes which I have given in the today's class. Okay, so the important synopsis which I have given under hybridization, please go through them once and try to recollect all the geometries which I have given under specific hybridization. So with this I am trying to close for today's session. That's all for today's class. Thank you. Have a nice day.